Traditional systems rely on external processors to handle visual input and decision-making. It's like your eyes being on one side of the room and your brain on the other, slow and disjointed. But this new neuromorphic chip changes that. It processes information the way your brain does, using something called the leaky integrate and fire neuron model. This allows the chip to react dynamically to light and motion, almost like a biological neuron firing in real time. Let's break down how it works. The chip is made from molybdenum disulfide MOS, a two-dimensional material known for its speed, electrical sensitivity, and flexibility at the nanoscale. It uses a spiking neuron architecture, meaning it doesn't process constant data like traditional silicon chips, but fires electrical pulses in bursts, just like biological neurons. It integrates visual sensing, processing, memory, and decision-making into a single component. No need for separate cameras, CPUs, or external memory banks. In practice, the chip can track hand movements and understand gestures in real time, reacting instantly to environmental input. It detects change in motion instead of processing static frames, improving response speed and energy efficiency. It performs object recognition, motion prediction, and gesture detection with over 80% accuracy in real time, using minimal energy. And most importantly, it does all this on the edge, meaning it processes data locally, not in the cloud. No lag, no data leaks, no delay. Where could this be used? In smart prosthetics, reacting to a user's intention the moment they think it. In autonomous vehicles, responding faster than a human driver could. In robotic assistants, able to interpret body language or mood and adapt behavior accordingly. In wearables like fitness bands that learn your movement patterns and predict fatigue before it happens. In drones that can adjust mid-flight to wind, light, or unexpected obstacles in their path. In consumer electronics, allowing devices like smartwatches or earbuds to understand gestures, mood, and environment context. Even more impressively, neuromorphic chips enable devices to operate without being constantly online. Imagine a robot assistant that can function entirely offline, making decisions locally, learning on the fly, and responding to human behavior without ever needing to ping a cloud server. That changes everything, especially for privacy, reliability, and energy efficiency. Imagine wearing smart glasses that understand what you're looking at and respond instantly. They could highlight an object, translate a sign, or alert you to a nearby hazard, all without needing Wi-Fi or a phone connection. That's neuromorphic computing at work. Now, here's where it gets wild. These chips don't just compute, they can learn. Over time, they adapt their behavior based on what they see, how you move, and how the environment changes. We're talking about robots that evolve, not just execute. Let's zoom out. This chip is part of a shift from centralized computing to decentralized intelligence. Instead of one brain controlling everything, imagine hundreds of tiny minds distributed throughout a machine, like neurons in a biological body. That means hyper-responsiveness, devices that react faster than human reflexes, personalization, machines that adapt to their user, not the other way around, resilience, no single point of failure. If one part goes down, others pick up the slack. Mobility without connectivity. This means smarter devices in isolated, remote, or high-risk environments, from disaster zones to deep space missions. We're also redefining how machines learn. Instead of training on massive datasets in the cloud, these chips can learn organically through real-world interaction, just like animals or infants. This has profound implications. Ethics. Can we hold a device accountable for learning something harmful if it wasn't explicitly programmed to? Security. If chips can learn on their own, how do we ensure that what they learn aligns with human values? Transparency. These systems aren't rule-based, they're behavior-based. That means we might not always know why they do something. This also means greater accessibility. Lower-powered, lower-cost devices can now include forms of intelligent behavior. Neuromorphic computing may democratize advanced tech, letting startups or individual creators build smarter systems without needing massive data centers. And it changes how we interact with machines. Imagine walls that recognize who walks in, tools that adjust their function based on how you hold them, public spaces that adapt to the flow of people like living organisms. This isn't just about smarter tech. It's about embedding cognition into matter. A world where every surface, every wearable, every machine part has built-in intelligence, not because of better software, but because the hardware itself is thinking. Imagine cities where traffic lights anticipate accidents before they happen, or classrooms where walls respond to student attention, or fabrics that detect injury and call for help. This isn't science fiction, it's the trajectory we're on. In the next 5 years, neuromorphic chips will appear in consumer electronics, wearables, and basic robotics. Devices will become more energy efficient and interactive, with minimal latency and personalized adaptation. Smart home systems will begin reacting to motion, emotion, and ambient signals without needing verbal commands. In the next 10 years, we'll see the rise of adaptive infrastructure, buildings, roads, and transport systems that think and respond. AI will stop being something out there in the cloud and instead become something you wear, touch, and live with. Real-time perception systems will dominate autonomous operations in cars, industrial robots, and personal tech. And beyond that, these chips could form the building blocks of artificial general intelligence, a form of machine cognition that's flexible, grounded in perception, and shaped by experience rather than rules. Distributed neuromorphic networks may blur the line between software, hardware, and biological intelligence, creating machines that not only compute but experience. From the researchers, this breakthrough shows strong potential for real-time, brain-like processing in future tech. A chip that lets robots think and react like they're alive isn't just impressive, it's a sign of what's coming next. This isn't just smarter tech. It's a step toward machines that blur the line between programmed and perceptive. And that future might arrive faster than we think. So what do you think? Is this the start of something incredible or something we can't control? Drop your thoughts in the comments. And if you're curious about AI and tech news, please like, subscribe, and hit that bell, because the future is just getting started.